Okay, so last lesson in chemistry, the reaction between acid and base. So that will be a neutralization reaction. So we've learned what acids are, we learned what bases are, we learned how to name them, we learned their properties. So it's time to mix them together and see what happens. And then after that, we're going to talk a little bit about acid rain. So first of all, a neutralization reaction is simply a reaction between an acid and a base. What you have is an acid, H something, in this case, in the example, is HCl, hydrochloric acid, plus something hydroxide. And in this example, it is sodium hydroxide. Okay, that's a base. When an acid mixes with the base, the products are always the same thing. You have an ionic compound, or we call it a salt, and water. Okay, so you can see that this is kind of like a double displacement reaction. The H from the HCl in red joins together with the OH from sodium hydroxide, also in red. And in the product, well, H and OH, that forms H2O. And what's remaining is the chloride and the sodium, they form sodium chloride. Okay, so that joins together, that joins together. Okay, so the general form of a neutralization is acid plus base, you get salt and water. By salt, it can be any salt, not just sodium chloride. There are many types of salts in this world. It's just an ionic compound. Okay, so you have to know the difference between a neutralization and a double displacement. A neutralization is a special type of double displacement. It is a double displacement between an acid and a base. Okay, so please make sure that if I ask you to label the type of reaction, you don't simply write double displacement when you see an acid with a base. It is neutralization. You have to be more precise. Okay, so any questions so far as to how this works? Okay, so acids and bases, they form salts. What is a salt? Well, salt is not just a thing in your kitchen. It is a class of ionic compounds. So many different types of salts. They are formed when an acid neutralizes a base. So you have sodium chloride, that's the salt we put on food. We also have road salt, that is magnesium acetate. That is not the same as your table salt. You can't put that inside of your soup. Okay, never mix them. They're used for different purposes. Do not ingest road salt. And this is the reaction that will form road salt. You have acetic acid, basically vinegar, and magnesium hydroxide. You actually have that at home if you have some antacid fluids. It's that white milky drink that you drink if your stomach is upset. You mix these two household compounds together, you will actually make road salt dissolved in water. Okay, so again, salts, there are many different types of salts. They're all called salts, but they're not all the same. Speaking of antacid, your stomach contains stomach acid. It's hydrochloric acid, actually. The pH is quite low, 1.5. Now, the reason that this acid is not hurting you, well, that's because your stomach contains a special mucus. Mucus is just things that are sticky and slimy that your body produces. Like, for example, you blow your nose, that's mucus right there. Okay, when you have phlegm, like something in your throat, that's mucus. And in the stomach, you have that. This is supposed to protect your stomach from your acid. So the acid doesn't burn through your stomach. Okay, problem is your esophagus does not have this mucus. So when the acid accidentally goes up the esophagus, that's going to burn, and that hurts. So this can damage your tissues. So that's what we call acid reflux. We can take antacid tablets or drink to slowly neutralize some of the stomach acid so that it does not hurt as much. Does that make sense? So that's the idea of using antacid. This is a neutralization reaction. The antacid is a base. Your stomach has the acid. You take it. The acid becomes less intense. You feel better. All right. And, well, what are antacids made of? Well, magnesium hydroxide is one example, or calcium hydroxide. These two bases are used as antacid because they're not very soluble. So they both have low solubility. They are terrible at dissolving in water. Now, why do we pick a base that is terrible at dissolving in water? What if you picked a base that was really good at dissolving in water? Like, I don't know, sodium hydroxide. Does anyone have any ideas? We use, actually, we use this equation, HCl, your stomach, plus calcium hydroxide or magnesium hydroxide. They neutralize, you form calcium chloride and water. This is okay. But sodium hydroxide is not okay. Why? Anyone explain what's wrong with ingesting sodium hydroxide? Nobody? Well, you've probably never seen sodium hydroxide. Okay, well, think about what sodium hydroxide is. It's a base. It is very, very corrosive. First of all, touching this will hurt you. Okay, when I was younger, I was working as a teaching assistant to another teacher, and they were doing a chemistry lab. Okay, I was responsible for handing out the sodium hydroxide in a pellet, and I accidentally got some on my hands. It stung, and I had to wash my hands afterward, and it left a red mark. Yeah, that's what happens if you expose yourself to solid sodium hydroxide in the aqueous form. That is still painful. So yeah, no, you cannot ingest sodium hydroxide because, number one, it is extremely corrosive. It will burn on your way down. Okay, the idea is to not get your stomach to burn. Well, ingesting sodium hydroxide will burn your mouth, your esophagus, and everything it touches. Bad idea. Another reason is that sodium hydroxide is very, very soluble. If you drink that, then it will neutralize your stomach. Okay, because it's so soluble, there's a lot of it in water, so drinking it will completely neutralize your stomach. You need stomach acid. You can't live without that, so you will die. So do not ingest sodium hydroxide because A, it is extremely corrosive. B, it is highly soluble, so you actually have a lot of it by accident. Calcium and magnesium hydroxide, they don't have that problem. Because they hardly dissolve at all, ingesting them will only dissolve a little bit in your stomach, so you're not really ingesting a lot of base into your body. Ingesting a lot of base is actually very toxic. So you don't want to accidentally neutralize all of your stomach. Okay, that is suicidal. You do want to just neutralize a little bit so it is not as painful. So please don't ingest sodium hydroxide. Just because we learned about neutralization in chemistry, you get some crazy ideas. Oh, I have stomach reflux. Oh, I know what to do. Don't. Okay, antacid tablets or a drink, that's fine. Do not drink your Drano. Okay, that thing used to unclog the sink. Do not drink that. That's sodium hydroxide right there. Okay, so let's do some practice with neutralization reactions. Again, you have an acid with a base, you get salt and water. So we're going to go through some of these together, and of course you have to balance them. So that's the challenge here. You have to predict what products are formed and what the answers are. So number one, you have HCl plus KOH. That one is the simplest of them all. All you have to do is write the salt and the water. So you would have that. Notice that H2O is formed from the hydrogen and the hydroxide. You have the Cl and the K. They form the ionic compound. the positive ion, the K, comes first. The negative ion, the chlorine, comes second. So KCl plus H2O. Okay, anyone with an issue with that one? Okay, let's do the second one together. The second one, you have this. H2O, where'd you get that from? You got it from the hydrogen from the carbonic acid. The OH, you got that from the hydroxide, from the magnesium hydroxide. What do you have left? Well, you have the CO3, the carbonate, and you have the magnesium, the Mg, and they form magnesium carbonate. And of course, you have to balance this equation. You have to put a 2 on the water because you need 2 of them. Okay, does that make sense, everybody? I'll do the third one, and I'll leave 4 and 5 for you guys. For the third one, now that's one of the special acid. You have acetic acid. You take the hydrogen from the back of CH3COOH, and you give that to the OH to make water. Well, what do you have left? You would have cesium for the CSOH. You just have the CS. That's positive. The rest of that acetate molecule, CH3COO, that is 1 minus. So that is cesium acetate, CS. And acetate is that polyatomic ion, CH3COO. So you would have that. Again, look at the 3 products for the first 3 questions. Water, water, and water. Okay, neutralization will always produce water. So if you're stuck, you don't know what to do. Well, write down water, first of all. You have to have that. What's the other guy? Well, that is the salt that is formed from the remnants after you remove the water, the positive and the negative ion. So I'll give you a few minutes. Do number 4 and number 5 and post the products into the chat, and I'll take them up in like 1 minute. So try to think about what will be formed, okay, and how to balance the equation. So go ahead, I'll give you a minute, and then I'll take this up. Anyone finish? Okay, you did the last one. That is almost correct. It is almost correct, not entirely correct, because the calcium nitrate is not a 1-to-1 ratio. Nitrate is 1 minus, calcium is 2 plus. But yeah, you got the general idea though. Anyone else? Okay, so that's the first one. It's, again, almost correct. I say that because it's not balanced, but the equation is right.
wait. Are we supposed to balance it too?
Yeah, you always
Okay,
have
I
to
can do
balance,
that.
like always balance your equation. Never leave it unbalanced. But yeah, you get the general idea though. Balancing equation is something else. We're learning how to find the products of a neutralization reaction. So if you can find the products, that's good for today. Okay, but make sure that you always balance whatever chemical equation that you come across. So okay, yeah, now it's correct. Now you've balanced it. So I'm gonna show you guys the answer. So that's the first one. There's a 3 for sodium hydroxide. There's a 3 for the water. You do need to balance that. Notice that the H and the OH, they form H2O. Na and the PO4, well, that is Na3PO4. PO4 is 3 minus. That's why you need 3 sodiums. Okay, for the next one, you have nitric acid, HNO3, plus calcium hydroxide, H2O, always there, and the rest of it, calcium, Ca, and the NO3. NO3 is 1 negative, calcium is 2 plus. You need 2 NO3s. Okay, for those that don't know how to do this, you do need a lot of practice. You need to ask if something isn't clear. Okay, you have to figure that out somehow, and one of the ways is ask, or find some ways to seek help, because this doesn't get easier. This isn't like biology, just memorize some stuff and you're good. You have to understand how you got those. There are many different types of neutralizations. You can't memorize the answers. You have to find the pattern and use that pattern to answer the question. If you don't know what that pattern is, you're not going to be able to get that. Okay, I'm trying to tell you what the pattern is. You need water. You need what's left after you remove the water. You remove the H from the acid, the OH from the base, whatever you have left. You put them together, positive first, negative second. You balance the charge for the ionic compound, and then you're done. Okay, please make sure you know how to do stuff like this, how to find the products of the neutralization, and how to balance it. Okay, do we have any questions? Okay, so let's move on to some applications of this. Why do we care about neutralization? Well, acids are everywhere in nature, and it's in rain, unfortunately. How do we get acid rain? Why is rain acidic? Well, because we, as a species, we release a lot of compounds into the air where it otherwise shouldn't be there. Okay, like sulfur dioxide, SO2, for example. You're not supposed to have that in the air. And nitrogen oxides, NO, NO, or NO, NO2, NO, even N2O, anything with N and O, yeah, you're not supposed to have that in the air. But because of our industries, we burn stuff, and those are residue gas particles that gets released. That goes into the clouds, and SO2 and the NOs, they will react with water in the clouds, forming sulfuric acid, forming nitric acid. So now when it rains, you don't just get water, you get acid rain. Okay, and acid rain is made up of sulfuric acid and nitric acid. Okay, does that make sense? So that's how you get acidic rain. It's from those factories that release these gases. And unfortunately, we have to do that. There's no way to shut down all the factory. So we got to find some ways to mitigate acid rain. The pH of the rain is usually a slightly bit more acidic. It's not exactly 7. But if it comes to a point where the pH is very low, like 5.6 or lower, then it becomes a serious problem. Okay, that is how we define acid rain. If the pH is 6, it's not a big deal. It's not 7, but hey, it doesn't hurt. So sulfur dioxide, SO2, is one of those gases. If you ever smell this gas, then I have bad news for you. First of all, it smells terrible. When you smell it, your body will naturally want to wheeze, and you will want to do that. It has this choking, disgusting smell. Sulfur always smells bad, and also that's a toxic gas. If it's getting that into your body, that will react with water inside of your body, and that forms sulfuric acid. That's bad. Okay, so sulfur, once you burn that with oxygen, let's say in a chemical plant, you would get sulfur dioxide. And we do actually a lot of this in Canada, a lot more in the United States, but we do it as well. We release a lot of sulfur dioxide via generating electricity and industries. So in that pie chart in 2004, you kind of have an idea of how much of this would release. Okay, so when you have the sulfur dioxide, SO2, that's already a toxic gas. That itself is a problem. It gets worse. It reacts with oxygen to form sulfur trioxide, which is also toxic. And then the sulfur trioxide will react with water, finally forming sulfuric acid. Okay, and sulfuric acid is battery acid. Imagine raining battery acid. That is actually a reality in some places of the world. In Canada, it's not so bad because, well, Canada has pretty strict standards for a lot of things, and we have a low population, so we don't need a lot of power plants. Unlike the United States or China, those are big countries with a huge population, so they definitely release a lot more. Most acid rain from Canada is probably due to the United States. Okay, we have a really industrialized neighbor. The US burns a lot of stuff. They pollute the air, and we share the same atmosphere. That comes over to Canada. We sometimes get acid rain, not very often, again, because we ourselves don't do a lot of that. So which is why we're trying to become more clean. We're trying to find cleaner approaches to generate electricity, not just for the climate, but for our own health. Venus is the second planet from the sun. We are on Earth. If you imagine what Venus must be like, just think about hell. If you read about hell or learn about hell, that's sulfur, brimstone, really hot, a lot of suffering. Yeah, that's Venus. You just described the surface of Venus right there. If you land on Venus, you probably wouldn't make it to the surface alive in one piece. The pressure on Venus is 90 times higher than the pressure on Earth, so the pressure will kill you. The temperature on Venus is like 450 degrees Celsius. You will be incinerated before you even reach the surface, so that will kill you. If you manage to survive that, well, good luck with the acid rain, because Venus has clouds of carbon dioxide and clouds of sulfuric acid. Okay, it literally rains sulfuric acid. We're not talking about the same type of acid rain as Earth. Okay, this is pure sulfuric acid. There's no water on Venus. At least on Earth, the acid rain is diluted by the water in the clouds, but no, that's a sulfuric acid cloud. So yeah, not a fun place to be. We landed some probes on Mars. Okay, Elon Musk talks about going to Mars. Like, Mars is our next destination. Who wants to go to Mars? It's a one-way trip, but who wants to go? Nobody says goes to Venus. Like, let's go to Venus. Nobody says that. Because we try to land probes on Venus. They got crushed by the atmosphere. So, it's not a fun place to be, and that's due to the carbon dioxide and the acid rain. Also, nitrogen oxides, NOx, they also contribute to acid rain. You can either have NO or NO2, and where do we get these? Well, factories, industries. This is a byproduct of a lot of the factories. The way that we generate electricity releases this. So our cars release this. Well, what happens? You have nitrogen gas under tremendous heat. it reacts with oxygen to form NO. That's bad. NO, nitrogen monoxide, will react with oxygen to form nitrogen dioxide. Already, this is very toxic. This is a brown gas that once breathed in will damage your lungs because it forms an acid inside your lungs. Well, it then reacts with the water in the clouds to form nitric acid. Okay, HNO3 is nitric acid, also a pretty strong acid, and this will fall onto the earth as rain, and it will damage crops. Okay, if the pH is low enough, it will hurt animals. Okay, does that make sense? So that's how you get acid rain. Sulfur oxides versus nitrogen oxides. Okay, they both contribute to acid rain. Okay, so aside from hurting plants, what does it do? Well, take a look at this picture. On the left, you have the statue of Abraham. No, that's not Lincoln. That is George Washington. Okay, that was from, I forget which year. I have it written down here. 1935 on the left, 1994 on the right. What happened? Well, it turns out that the statue is made of limestone, and limestone is calcium carbonate, CaCO3. Acid rain, sulfuric acid, once it drips on the statue, it will react with the limestone according to that chemical equation right there. You see that this forms calcium sulfate, which is soluble. It just washes right off, forms water, and forms carbon dioxide. Okay, this slowly eats away at the statue. So therefore, if you build a statue from limestone, you're going to lose that eventually. Okay, slowly, the environment, like acid rain, will slowly chip away at the statue until it's not recognizable anymore. Until you repair that, of course. The Statue of Liberty is made up of copper. That's not going to happen to copper, but if you're going to make a statue, don't pick limestone. That's a bad choice because acid rain will eat that away. Okay, we lose the statue. Big deal, right? We build a new one or just deal with it. Nobody died. Except in the water. If you are an aquatic organism, you really care about the pH of that water that you're swimming in. Aquatic organisms can only be adapted to a very specific environment. Okay, some like fish, some clams, shellfish, those things, amphibians. Okay, those things really need the pH to stay the same. If it rains acid, you're going to lower the pH of the water. And depending on which organism you are, you're going to be negatively affected to different extents. So in this little chart, you can see that, well, at pH 6.5, that's perfect. Everybody's happy. It starts to rain. pH becomes 6. I mean, not a big deal. At pH 5.5, the snails and the clams, their numbers start to decrease because they have difficulties forming their shells. They make their shells with calcium carbonate, which is limestone. Okay, the acid rain will eat away at their shells, so they have a harder time building a shell. Therefore, they have a harder time being alive. At pH 5, some other animals start dying, like bass, some crayfish, some mayflies. They all rely on the pH of the water. And then as the pH get lower and lower, more and more animals suffer. Okay, until once the pH gets so low, that lake will become dead. So as the pH decreases, the smallest and the most fragile will die first, and then the larger ones will follow if the pH continues to decrease. So we can't let this happen. There must be something we can do, because if you don't care about the fish, care about yourself. You eat fish. At least a lot of humans do. Okay, even if you don't eat fish, you eat things that rely on fish. So there's the food chain and the food web. We're part of the same ecosystem. because of our actions, we're causing acid rain. We're ruining it for everybody, including ourselves. So we have to fix it, right? How do we mitigate the effect of acid rain? Okay, and also in the oceans are being acidified, okay, every year. Every year it becomes a little bit more acidic. Part of the reason is due to acid rain, but there are other reasons, namely carbon dioxide in the air is increasing, that dissolves in the water to form carbonic acid. And same story, seashells, clams, these organisms will slowly decrease because it's harder to make the shell with more acid. And coral, they will eventually go extinct. Coral also has calcium carbonate. They cannot tolerate changes in the water. Okay. Change in pH, change in temperature, those are all lethal to the coral reef. And it's already too late unless we preserve them in an aquarium. Natural coral will slowly die because of climate change and the acidification of the ocean. Yeah, it's too late to stop that now, so that's quite sad. So enjoy them, enjoy the idea of coral while they can, while they're still here. They will eventually go extinct because of this. Okay, so how do you prevent things from dying? Again, you have trees, they are affected by acid rain. They destroy not just the leaves, they destroy the minerals in the soil. Plants need minerals from the soil. If acid rain comes, they mix with the soil, they react with the metals in the soil. That will become something different. Then the plants won't have them anymore. Okay, so they kill mature trees and they prevent younger trees from growing in the first place because it attacked the minerals that they need. So obviously acid rain is terrible. Let's do something about it. You have a lake, okay? You want to make sure that the lake organisms aren't affected by acid rain because you're out there polluting and you're making acid rain, but you don't want the creatures to die. You want to save SpongeBob. What do? How do you mitigate the effect of an acid? Well, easy, neutralization, right? That's what we're learning. So add a base to the lake. So let's dump a bucket load of sodium hydroxide into the lake, and yay, Bikini Bottom is saved. I have base in the water, so if it rains, they neutralize, you're fine. Is that a great idea, guys? Yes or no? Do you like it? No. Okay. If you say no, then you have some sort of common sense. Congratulations. That's like saying, oh, I have a splinter in my hand. Let me just chop off that finger. That's basically what you're doing. Oh no, acid rain is going to kill the animals? Well, don't worry. Let me kill them first with sodium hydroxide so that they wouldn't have to worry about acid rain. If you add sodium hydroxide or any powerful, strong base, yeah, don't worry. The acid rain won't hurt them anymore because they're already going to be dead. So no, do not add bases to water. Okay, especially not the lake. Instead, add something harmless that reacts with the acid anyway. Limestone. Remember the statue? Acid rain loves to eat away at statues. So why don't we just dump George Washington into the lake? That should do it. When the rain hits the lake, it will eat away at the limestone in the water, thereby sparing the fish and the crabs and the other things. Okay, so having limestone in the water acts like a natural antacid. It prevents the pH of the water from being too low because it will neutralize some of the acid once it rains. So that's usually how we do it. We add lime, calcium oxide. We add that to the lake because lime is that's not harmful to the fish, but it does counteract acid rain. So when you want to find the solution to a real life problem, you can't just look at the basic chemistry, acid, base. Well, let me just add a base, okay, because of neutralization. Well, no. you can't pick any base. You have to pick something that is harmless yet gets the job done. Just like you have stomach reflux. Do not chuck Drano. Okay, that cures the stomach reflux, but it causes a bigger problem. You see what I mean? So the same reaction that destroys statues, well, we found a good use for that. We can use that to save the aquatic ecosystem. So do we have any questions about this? Okay, well, that's the end here. I'm going to show you this video. This is the conclusion from yesterday's video. Basically, it's a neutralization reaction. I'm going to stop the recording first.